Is this working? Cool. There we are. It's a bit smaller. Let's see chat. All right, so test the delay here. And then hopefully we can get going soon. That works. All right, sorry if you had to watch me futz around with my drawing program there for a little bit. Just wanted to make sure everything was all lined up. So, okay, as you probably know, we're going to be doing a bit of sort of an introduction to category theory, aimed at hopefully people who sort of struggled with the subject before, kind of bounced off of it, and really just wanted to learn, but couldn't quite make the jump from some of the more concrete concepts to some of the more abstract. So with that in mind, yeah, let's kind of give at least a high level overview of what this sort of series of quote unquote lectures is going to be about. So some administrative notes first. If you saw the Slack post, I will be creating exercises for each one of these lectures, and these exercises will, surprise, surprise, be in AGDA. But the goal here is to really have people engage with the material. Because it's one thing to hear about concepts and to sort of think about them, but it's another one to really have to fight with it, to really wrestle with it until you feel like you have a really solid understanding. So I'm going to post a link to those. Now, if you have any questions about doing these, feel free to reach out to me via like email or Slack or Zulip or Carrier Pigeon or whatever you want. I just ask that you don't post the solutions online. It sort of really robs other people of an opportunity to get stuck, and getting stuck is how you learn, at least in my experience. So with that out of the way, if you want to use those, they're totally there, and I will provide support. And I would sincerely recommend that you do so. It's a great, or working with a proof assistant is a really great way to get a very solid working understanding of a concept as opposed to a more surface level one. However, for a lot of these lectures, I probably won't be using Agda. I do stream Agda on Thursdays, mostly just sticking around with whatever I feel like that day, but this will be pretty light on the live coding and lots of drawing and talking. So just get that out of the way. So on to the category theory. The first thing we should really be asking whenever we're approaching a new subject is not what is X, but rather why is X. So in that vein, why is category theory? Well, for me, the basic intuition is that we don't want to deal with sort of internal structures, but rather how they relate with one another. In doing so, we generally get a better understanding of sort of how a problem ticks, and it's much easier to sort of generalize and realize, hey, this problem, I've seen it somewhere. It's over there, and it's over there, and it's over there, and we can pull it all together and unify it into a single concept. It also has the added benefit of being a lot easier for computers to work with. Traditional mathematics, especially very set-based mathematics, it's tricky for computers to handle that. Whereas more categorical approaches, computers are quite good at handling that. So to lead this off, I don't know if anyone's seen Sandy's new book, but he leads it off with this quote from Dijkstra that I think is really insightful. And it is, "The purpose of abstraction is not to be vague, but it is to create a new semantic level at which one can be absolutely precise." So that is going to be what we're thinking about. Absolute precision. And that's what abstraction is getting us. So let's keep that in mind as things progress in these series of lectures, that we're not just doing abstraction for abstraction's sake. We're trying to really get down to the essence of what is a problem or a structure or anything. So with that out of the way, let's move on to abstract algebra, which is going to be the topic of this first lecture. Now, I'm assuming quite a few people have at least some understanding of some understanding of abstract algebra. And if you don't, please shout out and say so. At any point in these talks, feel free to yell out if you don't understand anything. Now, the basic idea of abstract algebra is quite similar to that of regular algebra. Surprise, surprise. And that's that we can solve problems symbolically. Now, that seems like sort of an obvious thing if you think about it, but it's really non-trivial. The fact that we can take real-world problems, sort of write them down in this series of symbols, manipulate those symbols, and then we get an answer out, and that answer describes the real world. That is surprising, and it only feels, not surprising to us because of, we've sort of grown up with this notion all around us that we can, adding and subtracting. That's totally trivial. Even a child can do that, but you do have to teach a child to add, and you do have to teach a child to subtract. And there definitely was a time where, algebra didn't exist. We couldn't think symbolically. And that is one of the most major advances in human thought across all of history, is taking problems in the real world and solving them symbolically. So if that's algebra, what's abstract algebra? Sorry. Can't see the chat totally. I need to rework my windows here. Embarrassing. I should know better. John Clark, good return Russell quote to a similar effect. Yes, I could go on with lots and lots and lots of these quotes. There's some growth and deek ones that are also. No, please do. That's why I'm running these things, so people can share and learn. So I totally welcome these comments. Oh my god. There we go. The screen's all working. So abstract algebra is taking this idea that we can sort of solve problems symbolically and saying, okay, that's interesting and all, but what if we examined the structure itself as a mathematical object? So rather than saying, oh, 2 plus 3 is equal to 3 plus 2, and that's interesting. Well, instead of adding variables to this and saying, oh, we can solve these equations, what if we really looked at plus? And how does plus behave? And can we extend this idea of sort of an operation to broader domains? And can we solve problems there symbolically? And the answer is a resounding yes. So to get started with that, let's talk about monoids. Now, a lot of people are probably familiar with monoids, or at least if you're Haskell adjacent, you probably have seen a monoid once or twice. But I will redefine them for those who haven't seen them. But if you have, I'm going to give them a bit of a twist, a bit of flavor. So a monoid is a collection A. We can think of this roughly as a set, but I'm not saying set for reasons that I'll get into later. An operation, A to A to A. An identity, A. Let's call this times, and let's call this E. Such that this multiplication is associative, and E acts as an identity to this multiplication. That is to say, x times dot y dot z is equal to x dot y dot z, and E dot x is equal to x is equal to x dot e. Now this just may seem like total gibberish if you haven't seen this before. So I find that generally the what of something is not the interesting part of a definition. It's the why. And I claim, let's answer this question then. Why is a monoid? Because there are lots of these algebraic structures that we can consider. I can whip up any amount of operations and any amount of laws, and we could study them. But we don't study all of them. We study a very small subset of algebras. So the question is, why do we study those? Why these over the other ones? And I claim that a monoid captures the notion of transformation on a set. That's sort of the core idea of a monoid, is that it sort of encapsulates symbolically what it means to transform a set. And that may seem confusing at first, but to illustrate this point, let's look at our multiplication operation. At first glance, this takes two A's and produces a new A. Now, I'm going to add a pair of parentheses here, and we're going to get a change in perspective. This is still the same type signature. We're just putting parentheses. But now we see, well, you give me an element of A, and I'll give you an action on A. Furthermore, if we look at our identity laws, left multiplying by E will give us an action. And that action is identity. And all the associative law says is that composition of these actions is also associative. So we have a one-to-one mapping then between an action, or an element of A, right? A. Or not a one-to-one mapping. We have a mapping into, oh, this is a mess. Into functions on A. So for each one of these elements in our set, we can derive an action on the set. Now, why is this interesting? Let's start a new slide here. This is interesting because it lets us reason symbolically about sort of the logic of actions, right? So any monoid you may see, let's say ints, right? Natural numbers and plus, right? As well as 0. This may seem to have, nothing to do with this sort of notion of transformation I was talking about. But let's sort of take our brains and shift perspective for a second. And what does addition do to the entire set as opposed to just a single point? Right? So we can think about the natural numbers as just a number line. 0, 1, 2, dot, dot, dot. What does plus 1 do to this number line? Well, it shifts each point over, right? So 0 goes to 1, 1, that goes to that, 1 goes to 2, 2 goes to 3, and so on. So we're shifting the entire number line over by 1, right? It's not just adding numbers together. If we just take our brains and shift perspective, we can see that plus is a shift as it acts on the entire set. And in a similar vein, we have multiplication, right? The positive integers, multiplication, 1. And this is the stretching, right? 1, 2. Let's try times 2 as our action. 1 will map to 2. 2 maps to 4, right? 3 will map to 6. So we're taking our number line and we're stretching it out. And all of these sort of laws around like, oh, well, we can commute addition and we can reassociate, it has an identity, that just means, again, these transformations, it doesn't matter if you shift, then shift, or shift by 2 and then shift by 3, or shift by 3, then shift by 2, right? And I think this is where a lot of people sort of struggle, both when they're learning algebra for the first time and sort of when you're trying to abstract further and further, is you get tied up in just this symbol shuffling and it all feels very arbitrary and it's like, oh, why do I even care about associativity and commutativity? I don't see the utility of this. When really these laws are describing sort of how things act on the set itself. So this is, not to go on a total detour here, but mathematics is not about theorems, it's not about definitions, and it's not about corollaries, and it's not about symbols. It's about sort of gaining new perspectives and new ways to think. And I would argue that the sort of core of abstract algebra is that we should sort of think as these sort of symbolic things as actions. And these actions can be thought of as symbols. They're sort of one and the same. So if we want to, we can take our very tricky problem about actions, shift to the symbol domain, do some symbol shuffling, and we get still a valid action out that's the same. So to make this sort of more concrete, we're going to need, or to formalize this notion of this translation in between monoids and actions, we're going to need a little bit of machinery here. This thing called a monoid homomorphism. Homomorphism. And you can think of this, the line that always gets trotted out here is that it's a structure preserving map. Okay, but what does that mean? Well, symbolically, we can think of it, if we have a map from a monoid M to a monoid N, then f of M times M is equal to f M times f of n. And f, the identity, is equal to the identity in n. Now, this may seem like a pretty innocuous thing. A lot of functions would satisfy this, but this is actually a rather strong statement. Because it's saying that, using our action perspective here, that the composition of actions in M, we can map those and get actions in N, and those actions also compose. So let's pull out an example here before we're getting too abstract. And it's an example we've all seen before, length. From a list of A to the natural numbers. Now, if you sort of sit and think about this, you should be able to see that how this works, right? So if we have length, xs cons, or append, ys, that's the same thing as length, t, plus the length of the y's. And furthermore, the length of the empty list is 0. So, as we can see, we sort of preserve this structure. Our length preserves the structure. No matter how you build up this list, and no matter what crazy ways, we're going to preserve this sort of concatenation operation. So we see these things absolutely everywhere. And once you kind of sit there, walk around with the definition for a little bit, really and sort of stew on it, you will notice that most functions you see in the real world are homomorphisms in some way, shape, or form. And the ones that aren't are generally the ones that are bad because they do surprising things. They break invariance, they break structure. I think it was Connor McBride, I don't have a source for this, but he said we should stop writing functions and only write homomorphisms. As that also lets us translate all of the reasoning we've done about M into reasoning in N, right? It sort of transports all of the all the proofs we may have made about M and all the thoughts we may have had about it straight into N. So, with that little bit of machinery out of the way, I claim that there, for any monoid, and M, there exists a structure-preserving map, so a homomorphism, into the monoid on M to M. So this is the perspective I was speaking about earlier, the sort of action perspective made formal. So we can take any monoid and think about it purely as actions. And I suppose I should back up for a second. The monoid on functions is just composition as multiplication, and the identity function as the identity element. And how do we write this function? Oh, furthermore, sorry, I'm getting ahead of myself. Furthermore, this function is injective. I'm sorry about my handwriting. I will try and slow down. I'm still getting used to this pen. So what does injective mean? It basically means we don't map two elements in the input space to the same element in the output space, right? We draw it visually. We have a bunch of points here. This can even be bigger than this one, but we just sort of embed A into B. So I'm claiming here that we have an embedding from a monoid, any monoid, into the monoid of functions on that monoid's underlying set. Now, how do we write this function? So let's try and write this one out. So first, let's call this homo m. Take an element of m, and we need to produce an element of m to m. Now we have a function that does this. Let's use Haskell notation here, just to make things even easier. It's multiplication on m, right? Because m's already a monoid. We can just straight up use the multiplication, and we get our homomorphism sort of for free, which is weird. And if we think about the conditions we had to show before, we need to show that homo of m times m prime is equal to homo m composed homo of m prime. Clear that up a little bit. So let's break this down even further. Replace that composition, running out of space here, with just a function call, and expand out the definition of homo, right? So this is just the same thing as m append, partially applied. That called upon m prime append is the same thing as calling it on m prime. Running out of space here. M prime append. I might have to write that. Give myself a little bit more space. But if we just unfold the definition, we should see it's true by just associativity on M right here. And identity should be relatively easy to see as well. Homo of E is equal to E acting, or partial application of the multiplication, and E, which is just going to be identity, right? Sort of trivially, you multiply the identity element by something, you're going to get the same thing out. So we've sort of proved our first theorem here, and that theorem goes by the name Cayley's theorem. You may see it phrased slightly different with this notion of submonoid and blah, blah, blah. But this reifies this idea that we've sort of been discussing as a monoid embodying the notion of a transformation. And this is sort of what's going to lead us into category theory. So let's draw a little picture, right? So let's say we have I don't know, the monoid true or bool or, and I'll use the programmer notation for or and false. think about it for a little bit, you should be able to convince yourself, yes, this is the monoid. We got two elements in bool, right? So what are these? These correspond to true. And these are true and false. Now let's apply Cayley's theorem, this theorem we just proved, to view this as actions on bool, right? So we have true multiplying. This maps to true, multiplication by true. This maps to multiplication by false. And these are both of type bool to bool. So let's draw a picture now. And for those who've seen category theory, you might kind of know where I'm going here. You've got multiplication by true or false. And we've got multiplication by true. I'm just writing the same thing here, just more diagrammatically, right? We're drawing a picture instead of using words, which can really make things clearer. Now, you may ask yourself, it's sort of a natural question to ask if you sort of sit and think about this for a while. Well, what if we could have this sort of same notion of the algebra of transformations, but instead of only acting on one object or one set, be able to have functions like a to b, you know, not just restrict ourselves to functions of the form like that. But these transformations should still compose in the same way that we'd expect their monoid transformations to. It shouldn't matter where we put the parentheses, which matter we do order we do the composition, and we still want a notion of identity. Because this not only lets us talk about, you know, doing nothing, which has its own virtues when you're doing things like folds or what have you. You need to summon an element from the void. But also sort of lets us reason about things like inverses. It gives us a more internal notion of doing nothing. So for example, taking a slight detour, probably unplanned, there's this notion of a group. We don't see these that often in programming, but they're absolutely everywhere in math, which is a monoid with inverses. That is to say, there is a operation called inverse, which takes an element of, it's called a group G to G, such that G times G inverse is equal to identity is equal to G inverse G. Now, you can really start to see the utility of the notion of identity here as a tool of reasoning and not just as a tool for being able to summon, I don't know, use an empty element for a fold or something. We can start to express algebraic laws quite nicely by sort of calling out to the notion of doing nothing. In the same way that the invention of zero let people sort of invent, you know, algebra and all these other fancy concepts. We too should be able to use the notion of doing nothing to be able to gain ourselves some reasoning power. So we'll get back to groups later. There's a lot you can say about groups, but for now I will just leave them as an example for why we might want inverses. So keep popping up back the stack. Man, this is slow to undo. Man, erase. What was I talking about? That's right, categories. So now that we've seen this notion of, is this the pen? No, that's not the pen I was using. not it. Is this it? No. Is this? Yes. We want to talk about not only the sort of algebra of actions of A to A and how they compose. We want to talk about the algebra of actions A to B. And we want them to behave the same way that our monoid actions do, because they seem to capture the notion of transformation quite well, as we've seen by our theorem that we sort of informally proved earlier. And that leads you very naturally to the notion of a category. So a category is a set, collection. Let me be clear about this collection thing. Collection of objects, quote unquote, a collection of morphisms between objects and we will be denoting these like so. This dot is an object, call it A. This dot is an object, call it B. We will denote this arrow as F. And this sort of takes the place of those arrows I was drawing in the monoid case, where this is the underlying set of the monoid, M, and these are E and M. And we're generalizing this to multiple objects, or multiple points, if you will, such that, we have, getting ahead of myself, an operation called composition, which takes a morphism B to C and a morphism A to C, or to B, and produces a morphism A to C. So the notion here is that we should only really, in the monoid case, we could compose transformations willy-nilly. But in the more general case, we only want to really be able to compose things whose ends, quote-unquote, match. And we'll be getting to a concrete example here soon that I'm hoping will clarify things a little bit. Such that composition is associative. It doesn't matter where we put the parentheses. And we have an identity arrow, ID, A to A, and ID acts as identity to composition. So for any F, ID compose F is equal to F is equal to F compose ID. So let's take a breather here. This was a lot of writing. All we've done is just written out formally this notion of taking our sort of composable transformations on a single object. And now we have composable transformations on lots of objects. That's all we've done. So I hope that clarifies there as to why is a category. A category just aims, don't want to sound like a broken record here, but I really want to hammer home this point. A category aims to capture the notion of composable transformation. And there are, of course, some weird edge cases that you can think of that kind of don't feel like it. But that's where the idea came from, historically. And it is useful to keep that in the back of your head. So, some examples. Well, we were speaking about monoids and homomorphisms before. Those form a category. So our objects are monoids. And arrows are structure-preserving maps. Preserving maps. All right, let's just write homomorphism. Homomorphisms. So another example is something like set. Sets are objects. Functions are morphisms. And there's lots of riffs we can sort of do on sets. What if we did like Haskell or something? It's the category of Haskell types and functions in between them, even though if you wave your hands enough, it's a category. But I'm going to present sort of a more pathological example. But before doing that, I want to just take a moment to take a breather and ask if anyone has any questions or is confused by anything or wants clarification. Because I know I threw quite a bit at you there. It's a lot to ask someone to absorb all at once. So if you do, feel free to shout out in the Twitch chat or something. Yeah, because this is how I sort of think. It's very hard to. I don't like going, oh, look at all these examples. Oh, let's just pull an abstraction out of our butt. I never find that approach extremely motivating. Like people come up with abstractions they're trying to capture like the essence of something. So it's a good idea to lead with that, as opposed to have someone stumble across it later and be like, oh my god, Cayley's theorem, what? This is so cool. This all makes sense now. Yeah. So we've got no more question. Oh, jumbled bag. Yeah, that's a good one, and that sort of it works rather well with the way you actually perform category theory when you're trying to prove theorems and stuff. Is you just are sort of shuffling around these pieces with some laws, and certain pieces only fit together, and certain pieces are equal. And you just kind of play with them until you get the answer. And that's really where the power comes in. When you can, yeah. It's a really easy jigsaw puzzle. Yeah, it's a Rubik's Cube with only one little piece. So hard. So, how's it going? Yeah. Another example is let's take another slight diversion and define a preorder. All right. So, why is a preorder? Now, humans have this sort of built-in desire to say one thing is better than another, right? Like I was watching Vlad's stream earlier today, and he was doing a tier list of programming languages, and I feel that's just sort of a very indicative example of this very deep human drive to put things, in a big pile, and one thing's above another, above another, above another. So a preorder just aims to capture that notion. A notion, try to capture the notion of bigger or better or smaller, or really any other sort of word you can think of. If it's an it's probably a preorder. So, yeah. I didn't mean to do that. So basically, we have a set, right? Let's call it A, and a relation, which is I'm not going to talk about. Sort of, what's a good way of putting this? That doesn't involve a big, a notion of A, B for A, B in A. That's a terrible in sign. So we've got this kind of suggestively named less than or equal to, but we still have to give it some laws. A is less than or equal to itself, that is reflexivity. And if A is less than or equal to B, and B is less than or equal to C, then A is less than or equal to C. Transitivity. And if we go back to sort of the motivation behind the idea of a preorder, you should be able to see sort of why these rules exist. A thing is at least as big or as small or as better as itself, at least. And if C is better than B, and B is better than A, then C better be better than A, or bigger, I suppose is a better way of putting it. So this really just captures, a notion that you could sort of come up with on your own. Nothing really shocking here, but exactly, and that's a perfect example because you came across points where you had apples and oranges, and you had to compare coq with, what was it, like JavaScript or something, or is it? Oh man, I'm forgetting what it was. Two programming languages that were like totally different, and it's sort of an absurd question to ask. Oh, do I like CoffeeScript or Agda more? Like they're totally different tools. So that doesn't necessarily mean that A is less than or equal to B, or B is less than or equal to A, right? We don't need to be able to compare apples and oranges. We just have to have a notion of something is better or bigger than the other. JavaScript is the initial object in the languages. What's the problem? Yeah, actually, there's a preorder of programmers, and 10x programmers are at the top. You see, we are all beneath them. We are all lesser. If only we all were as good as those 100xers on Hacker News. Yeah, enough about Hacker News. So if you sort of squint at this, you can see where I might be going with this and why I'm talking about preorders. We have a notion of an arrow, less than or equal to, right? We have a notion of identity. A thing is less than or equal to itself. And these morphisms, or these less than or equal to's, compose. So a preorder is sort of trivially a category. And the reason that me and everyone else sort of brings up this example is categories were initially motivated by the idea of capturing the notion of composable transformations, but the morphisms need not be functions. They don't need to have any sort of like computational content. They don't need to do anything. They could just be sort of abstract notions of less than or equal to or greater than or equal to. It doesn't necessarily mean that your morphisms are functions and that you can call your morphisms. And it's important to keep that in the back of your head whenever you're doing sort of category theory abstractly. You can have as your mental model like functions or whatever, or the category of monoids, or pick your favorite category. We'll cover quite a few in this sort of series of lectures. Uh, but Hask is not the only category. It's sort of the roundabout way of what I'm trying to say. There's lots of others, and they may have more or less structure. This is important to motivate some of the things we're going to talk about later. So, charging right on ahead. So monoids, we had a notion of structure preserving map, right? A monoid homomorphism. So it's a natural question to ask, well, what does that look like when we have categories as opposed to monoids? So monoids with lots of objects. And of course, there's an answer. It's called a functor. Now, I love Haskell, but if there's one thing I'm not a huge fan of, it's how it gives people sort of this idea that, oh, I see the word functor, I know what it means. It's a much more general notion than that. Functors in Haskell are in between only one category, whereas a functor here is in between two categories. Is a structure preserving map between categories. Two E's categories. So you can note this C to D. Now this was easy to define with monoids because a monoid is just got like a set, and we can define the map as a map of objects of the set, right, or elements of the set. But categories sort of have two types of data in them. They've got objects and they've got morphisms. So a functor sort of needs to act on both. So we have an action on objects, which takes objects in D, denoted C.obj. Also one variant in one argument, which has to be the last. Exactly. It's great that it acts as an introduction to this sort of modes of thought and ideas, but it can be a bit limiting if you see the word functor and say, yeah, I know that. I know, honestly. Why aren't we all programming in category theory directly? For shame. And I'm going to introduce a bit of notation here. So when I want to write a morphism in a category, I will write it like so. Don't monoid simultaneously. Yes, but the way we define monoid homomorphisms in sort of traditional abstract algebra as opposed to categorical algebra is we only talk about the action on elements, because the elements are in a one-to-one correspondence with the actions on the set, which is what Cayley's theorem says. So if you talk about the action on objects or elements in the monoid, then that's sort of the end of it. You don't need to talk about the action on morphisms. So we have a map on objects and a map on morphisms. So this means we take, so let's say we have a category C. Let's draw a better category. So we all know categories are blobs with lots of dots in them. A, B, and we have a category D. Oh yeah, you could totally ask. This is why I'm running these streams, to sort of act as to do something with the stuff I know about category theory. So yeah, if at any point you have any questions, shoot, and I will do my best to answer them. Just know I might say I don't know. So Ishi's factoring a binomial. I don't want to get super into sort of more regular algebra, but if you want to, you can send me a message on like Slack or Twitch or something, and I can answer that sort of out of band if that's okay with you. Elements of the monoid, morphosomes. Yes, that is correct. Assad. Yes. So that you can view a functor that way as having an action on both objects and morphisms. But that's sort of implicitly applying Cayley's theorem. It's the point I was poorly trying to make. So if we map these to F A, I'm going to always denote these with F0, unless I run out of space. B, and let's call this F, and this is F1. So you can sort of see how this takes the structure of A and sort of plops it into D. Now, it does still have some laws in much the same way that monoid homomorphisms have laws, such that the composition of two arrows, so if we have, say, like F1F, compose F1G, this should be the same as composing F1F compose G, and F1 of the identity arrow is just equal to the identity arrow in G. So this may seem, again, like quite a bit to sort of digest here. And it really is, but hopefully we can see a couple of examples that might help to illuminate this concept. So let's move on to this page. So let's pick a good one here. The first example of functors we're going to look at are things like, so we have the category of monoids, right? And the category of sets. So we can sort of trivially take a monoid and just like forget the fact that it's a monoid, right? And just return the underlying set, right? So that's our action on objects. Action on objects. Objects is going to be forget we are monoid. Are a monoid. So after all monoids have a set of elements, right? And for action on arrows, which, as a reminder, are monoid homomorphisms, we're just going to forget the fact that they're homomorphisms, because they all have functions underlying them anyways. So action on morphisms. Morphisms. Forget we are a homomorphism. Fism, that's a long word. So you can kind of see how this might work, right? We take, obviously it preserves composition, right? Because composition of functors in one is composition of the functors in the other, and the identity homomorphism, its map is just identity. So it is a functor. So let's call this, I don't know, forget. Now, let's pick a little bit more of an interesting functor. One from the category of sets to the category of monoids. So what does this mean? Or what do we need to do this, to construct this? Well, we need for any set, for any set A, I need a monoid on A. Now, this seems like a pretty tall order. Or I need not a monoid on A. I just need a monoid. Yeah, this seems like a pretty tall order. Like, how can we just, for any set, just pull a monoid out of our hat? And this is truly a hard question to come up with an answer with, so I'm going to cheat and tell you what it is. Or I guess not tell you, but I'm going to lead you down a path. Let's consider lists. Consider lists of A's. We can append lists, right? So we take two lists, or append. I need to get more organized for this. Takes two lists, and returns a list. And there is an empty list, right? And you squint at this and think about it for a little bit, you will see that it's a monoid. More importantly, for any A, we can construct, the list of A's, right? So we have our mapping of sets to monoids here. And this when I was first learning, this really wrinkled my brain. And I just kind of sit there and think about it there. And think about it quite hard. Because I think that if you're sort of, I'm making the assumption that most people who are watching this are at least roughly familiar with Haskell and have probably tried to learn a little bit of category theory in the past. So if that's incorrect, please let me know. But when I was first learning this really, I struggled with this quite a bit. And I think it's because Haskell sort of obscures what's going on here. So let's think about this, and I'm going to use some new notation here. Hopefully, if it doesn't make any sense, let's explain it. So for any a set, I need to produce a monoid. Or that's not quite the right way to describe this, I'm sorry. I can produce a list of A's, right? Or a type, I suppose is the correct notation to use here. Type / set. And that mapping will be A to list of A. So this may not feel like a, in Haskell we would just denote this with the sort of type constructor list. But that really obscures what's going on here, in that the list type constructor is really a function from types to type, right? And now in Haskell, this sort of operates at like this kind level and blah, 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 blah. But if we're thinking about dependent types here, which you should be if you want to do the exercises, because they are written in Agda, we can see that this type constructor list is just a function, type to type, right? Now, or using our notation, set to set. So the set of A to the set of lists. So with that in mind, this list constructor is totally valid as a map of objects, right? Because we take an A, 2, A, which is a set, 2, a type, or yeah, type, whatever, to a set. I can never decide on the notations, or what I'm going to describe types of sets as. And that set is equipped with monoidal structure, as this map actually maps A. List of A. This should be monoid. My bad. Plus, and empty list. Producing an append, yes, but sort of by virtue of picking list, this is really like a dependent record or a dependent product type. So, yes, the object mapping of the functor is also supposed to pick out sort of an append operation and an empty operation. And this is made more clear when you're working in sort of a proof assistant. All the sort of mechanisms of this unfold. And sadly, or I guess not sadly, I'm making surprisingly good progress. So the exercises haven't quite gotten to categories yet. I linked them earlier in the chat at the very top if you want to take a look. I believe they cover up to Cayley's theorem. And hopefully they're at a decent level of difficulty. They aren't too hard. But if you do have questions, please shoot me a message on whatever channel you choose. Please don't post the exercises, the answers online. So a mapping of, so now we have our object mapping, right? We map A to list of A, append empty list. So now we need a mapping. Of morphisms. So in set, morphisms are just objects. So we need to map F, which is a map A to B. We need to map that to a map list of A to list of B. So when I write this is sort of like a function type, right? And this is describing the actual action of the function. So this guy would have a type signature that's set to monoid. And this is the actual body of the function. I could also, write this out like, I don't know, hinge set to monoid, and inj A is equal to list of A plus and empty list. So this notation and this notation are equivalent. I just have to write less to write this one. So if you guys find this super annoying, please let me know and I will stop doing it. But it's just a notational convenience that makes it slightly faster to write. You'll probably see this quite often in the literature too. So it's a good thing to start getting used to. So yeah, we need a map from F, which is on A to B, to a map of list of A's to list of B's such that this resulting map is a homomorphism. And if you know a little bit of Haskell, you should be able to construct this function pretty obviously. It's just mapping over each element of the list. We take F and we apply it to the first element, the second element, third element, so on and so forth. So it's just F goes to map F. And if you think about it, you should see that this resulting map is a homomorphism, right? Like if you map and then append and then map, it should be the same thing as appending them both together and then mapping over the resulting list. And mapping the empty list is obviously just going to result in the empty list. So map is a homomorphism. And furthermore, if we sort of think about our rules from before, that is F1 goes to F1, and G is equal to F1, F compose G. So you map over the entire list with G, and then you map over the entire list with F. That should be the same thing as mapping over the entire list with F compose G. If that's not obvious, let me know, but I think it's, thinking about it for a little bit, it should become clear. And mapping identity is the same thing as just doing nothing to the list. Yeah. So our functor laws are satisfied. No, I'm writing a lot in black. Let's give ourselves a nice green check mark. Shoot. So we've seen two functors today. Monoid and set. There's a very boring one. That just forgot the fact that we are the monoids are monoids. And we see another one. Let's call this functor list, which takes any set and produces a monoid. Now there's a relationship between these two, which I will get into later. And it's quite interesting and leads you in lots of interesting directions. And if you know a little thing about category theory, which I know some people in the chat do, you know what I'm talking about, but that's for another day. For now, I just want to take a little bit of a break and sort of see where if everyone's good. And then I'm going to move on to talking about the exercises a little bit. So I'm just going to grab some water. I'll be right back. All right, I'm back. All this talking dries out your throat. So that probably will conclude the sort of more lecture-y part of this stream. Let me just check my notes. Yep, that looks good. But did we show that the functor maps any function to a monoid? Yes. Yes, we did. Basically, I did breeze over it pretty quickly because it's the sort of thing that if you think about it for maybe 30 seconds to a minute, it should become clear that if you, let's open up that slide. If you say, I don't want green, I want black. So it's like map f xs cons map f y's is equal to map f xs or append-wise. And if you stare at this and think about it for a little bit, it should be pretty clear that that this holds, and mapping f over the empty list. Forgot to write the rest of this. Map f over the empty list. It's still the empty list. So map doesn't change the structure whatsoever, which is exactly what we need for a homomorphism, is a structure-preserving map. And there you go. So yeah, I probably shouldn't have breezed over that as quickly as I did, but yes, it is a homomorphism. Okay. Do we have any other questions before I? Yeah. This category stuff. It's pretty cool. Do we have any other questions before we move on to the just sort of discussing the exercises, kind of taking a look at them, and talking a little bit about AGDA? In that case, I think I might futz with OBS for a little bit to get Emacs open, and then we can sort of do a bit of discussion on sort of getting AGDA working, kind of what is AGDA to begin with, if you don't know that, and sort of how to complete the exercises and where they are. So again, I posted these earlier in the stream, but for people who may have missed that, you can find the... Oh, shoot. I missed that. Yeah, why is AGDA? That is an excellent question. I accidentally opened my own stream. I missed that. Yes, so why is AGDA? That is actually an excellent question. You're learning. You're learning. So AGDA is... the idea here is that we want a computer to be able to check our proofs, which may seem like an intimidating idea, but for me, I find it to be very valuable as sort of a learning tool, especially for when you're self-learning. Because a lot of the difficulty of learning mathematics is knowing if you're even doing the right thing. So if we have something, it's a computer system to check if our proofs are correct, you know you're not just going off into the weeds and constructing an invalid proof or your proof has errors. It keeps you honest. So there are other proof assistants out there, like Coq and Lean are some other big examples, and there's lots more. But I find, just for myself and talking to others, that AGDA is a bit easier to sort of grok if you already have Haskell experience, and it's a lot more explicit in a lot of regards. There's less proof automation, which is bad in certain circumstances, but good if you're really trying to get down into the sort of inner workings of things and get a really solid intuition of how everything works, as opposed to just typing in auto and praying. So, futz with come on. Today is the day that my Emacs theme broke. So I have to install that real quick. But where is Emacs? You get to see me fix my Emacs config on the fly. If it's going to work. Something's up. Oh, there we go. Package. Oh my god, that's so slow. It's probably because I'm streaming. You know, we can live with the default Emacs theme, I think. It's not that ugly, right? It's pretty ugly. Exercises. So if we take a look at the first set of exercises, should be able to find that in that repo I linked. It's called Lecture 1. We have a little bit of boilerplate, just defining a monoid. Shouldn't be, because it's not Vim. Yeah. This Vim script is so much better. I'm kidding. I used Vim for years and years and years and years. I just got sick of it after a while. All right, so now that we've loaded ACT up, you can see sort of there are holes for every exercise. And if you're using Emacs, you can hit Control-C, Control-Comma to get sort of the type of the hole, and you can work from there. I've left some examples in here that you can kind of work off of. But if you're not familiar with Emacs at all, I did not provide an introduction to Emacs because Philip Wadler did a better job than I could ever hope of doing with Programming Language Foundations in ACTA. You don't need to read the whole thing. Section 1 ought to be enough. And you don't even need to read all of that. It should be enough to get you going. So if you want to take a crack at these, I would really recommend it. And I'd love feedback, sort of both on difficulty level and sort of the content. Was it interesting? Because I plan on releasing sort of exercise sets along with each one of these lectures weekly, so that people can kind of work along and get a bit more hands-on experience and not just get talked to by a guy on a screen. So yeah, there's quite a few. I think we've got yeah, 6 exercises, and it concludes by proving Cayley's theorem, and one of my favorites. So it's not just like, oh, is this thing associative? There's some real mathematics in there, and you're actually doing theorem proving. So hopefully the people find that interesting and valuable. And with that, I think that concludes lecture 1. So I think next week we will be talking a little bit more about preorders and lattices, and sort of leading into a discussion on limits and also adjunctions, if I can get that far. So hopefully moving at a good pace here. So yeah, that should be it. Now I'm going to hang around here for a little bit more if anyone has any questions they want to ask, or I don't know, just sort of anything. So now is the time. If you got it. I'm going to try and get my theme working in the meantime. Oh, and on the exercises, I think I've already mentioned this already. Slipped my mind earlier. Please don't post solutions online if you do solve them. Yeah. I mean, if you want to stream the solutions, I guess that's okay. I just don't want people to be able to easily Google these things and just get like an out. Yeah, no worries, dude. All good. Yeah, I'm excited about it. I've been meaning to do something like this for quite a while, and I always struggled with writing about it. I don't know. I just think that it's much easier to communicate ideas just sort of verbally. It's a lot more informal. You can ask questions. It's a lot easier to digest as just sort of like in the background or something. So I think it's a good format. Yeah, and I plan on not stopping at just like adjunctions. I want to go quite far with this. At least make it a solid way into sort of categories for the working mathematician. And maybe once I get probably, I don't know, in this section, up to like section 7 of categories of the working mathematician, I think I might just kind of, we might diverge and just do whatever. Probably a bit of topos theory or something along those lines. Though I'm open to requests there. So yeah, that's a long ways off though. We still got, I mean, we did cover quite a bit today. Okay, maybe not. We covered the first 7 pages of categories of the working mathematician, and we have about 188 to go. So at this pace, it'll probably take about half a year. But yeah, making better progress than I initially anticipated. I thought I would just get up to the end of monoids today, but we did categories. That's good. And functors. Graph box. Oh, I want Doom graph box. Yeah, let's see. What else am I thinking of? Doom themes. That's the one I want. The theme. And I want Doom graph box. Oh my god, so much better. That default Emacs theme is truly horrible. I don't like many of the Emacs defaults. Just atrocious. How anyone thinks Control X, Control S is good is fucking beyond me. All right, so I think unless anyone has any more questions, I might be signing off for the day. But I plan on doing this every Monday around 5 p.m. Pacific Standard Time, and I also do more Galaxy Brain stuff on Thursdays if you want to tune in for that. It's more Agda heavy, and more of me getting confused by type errors than this will be. But I still think hopefully it's entertaining to some people, because it's entertaining for me to do. So without any ado, I think this went well. So I think I might be signing off for the day. And I hope everyone found this valuable. And I will see you all hopefully next Monday at 5 p.m.